Okay, today we're going to continue on with some more discussions on area. As a matter of fact, most of the unit is on area. Today we're going to be looking at areas of regular polygons. Okay, what you're going to find with regular polygons, first off, we're going to get a new formula, probably a formula that nobody's ever seen before, or you may have seen it on some previous formula charts, but maybe didn't know what it was, so we may not have paid it much mind. We're going to get a new formula. And one of the things you will see is that your calculations are probably going to be a little bit more complicated than they have been in recent days. So let's start having a look here. Okay. Now, basic reminder here, definition of regular. A polygon is said to be regular if it is both equiangular and equilateral. That's from about 3 months ago when we first saw that word. Okay. But we do have some new vocabulary when it comes to looking at regular polygons. Okay, this vocabulary will most likely be at least new in the way that we're going to use it. So you may recognize at least one of these words. I know you'll recognize at least one of them, but we're going to use it a little bit differently than you've ever seen it before. Okay, first off, definition: the distance from the center point of the polygon to a vertex is called a radius of the polygon. Now, the word radius is obviously not a new word to us. We just got out of a unit dealing entirely with circles, so we heard the word radius plenty of times. But what we probably have never considered is the possibility that a radius might exist in other types of shapes rather than just circles. And if you want to get technical about it, what the term radius means is longest distance halfway across. Okay, longest distance halfway across. So if you put a radius into a regular polygon, it's going to start at the center of the regular polygon, just like it did with a circle. It's going to extend out to the perimeter, just like it did with a circle. But in these cases, it's going to go the furthest distance that it can before it ends. And that will happen by extending out and making contact with one of the vertices. Okay, so that's how come the radius goes out to one of the corner points. Now in a circle, we had an infinite number of radii because the radii could go any direction they wanted because it was the same distance any direction it wanted to go. It was the same long distance in any direction. Obviously, if we're talking about a regular polygon, we don't have infinite radii in a regular polygon because there's only certain places that the radius can go to in order to achieve that longest distance, the corner point. So if you're dealing with a regular quadrilateral like this guy on the left, there's only 4 radii in there. The pentagon in the middle, there's 5 radii in it, and the hexagon, there's 6 radii in it. You're going to get the same number of radii as you have sides, numbers of sides in your regular polygon. Okay, so the word radius, we've probably seen it before, but probably not in a regular polygon. That brings us to another term, and this is one that we probably do not know. The distance from the center point of the polygon directly to a side is called the apothem of the polygon. Okay. And basically, again, if you want to get technical about it, apothem measures the shortest distance from the center point of the polygon out to the perimeter. The shortest distance. So the radii measure the longest distance, which is out to the corner points. Apothem measures the shortest distance, which is directly over to the sides. That's how come our apothem forms a right angle with the side of the polygon when it makes contact. And just like with the radii, there are not an infinite number of apothem inside of the regular polygons. There will be just as many apothems as there are sides in your polygon. Okay, now that's going to bring us to the formula. The area of a regular polygon is found by the formula 1/2 times A times P. 1/2 times A times little p. Little a represents the apothem. Little p represents the perimeter of your regular polygon. Now over there on the side, I put formula chart question mark. Okay. Once upon a time, this was on the tax formula chart, and then it vanished. I'm not sure if it's going to reappear or not. And I cannot find a star formula chart that shows it yet either. Okay, so probably what we need to assume is we need to assume that we're going to need this formula. We're going to assume that the chart is not going to give it to us. So this is one that we're going to get memorized. If they do happen to give it to us on the formula chart, I guess that'll be Christmas and we'll be happy that it's there. But we're going to assume that it's not going to be there and we're going to memorize it just in case it does not show up. 1/2 times the apothem times the perimeter. Very simple formula. Not a lot of information going into it. But as you're going to see, sometimes getting that information can be a challenge. Now, the reason I brought in the apothem and also the radii into the problem, because if you notice, if you look at the formula doesn't have anything to do with any radii in the polygon. Okay, so if you're wondering why I bothered to tell you about radii, well, here's why I bothered. In a regular polygon, when you bring the apothem and a radius into the problem at the same time, pretty easy to see you've got some right triangles in there. And as we've been seeing for the last day or so, wherever we have right triangles, that means we're going to have Pythagorean Theorem. That means we're going to have SOHCAHTOA, and those are going to be our tools to help us find missing information so that we can fill in the missing blanks inside of this formula. Okay. So one important aspect of the apothem and the radius in a regular polygon is that they together will build right triangles that also include half of one of the sides of the regular polygon. Okay, so given various information either on the perimeter of the polygon or the apothem or the radii, we're going to be able to calculate all kinds of different stuff inside of there. Okay, so this fact will be useful when searching for the length of the apothem as well as the length of the perimeter. Okay, now before we get into some specific examples, I do want to introduce you to a couple of special shapes. You don't particularly need to write all this down. I'd kind of like your undivided attention on it. I'd like to talk you through a couple of shapes. Okay, there's a couple of really special shapes that we need to become pretty familiar with. There's a lot of little connections that can be made inside of them. One of them is the regular hexagon. Okay. Regular hexagon. So we've got a six-sided figure where all of its side lengths are the same and all of its angle measurements are the same. And I'm going to run through this real quick. So if you're taking notes, you may need to pull this back up on Edmodo, look at it again later on. Something special happens in a regular hexagon when we draw in all of the diameters. And I'm using the term diameter just like we use the term radius, okay, going across the figure, making contact with the corner points. Okay, so there, all of the diameters are drawn into our regular hexagon. Now, think about what it means to measure all the way around inside of a circle. 360 degrees, right? So if it's 360 degrees to measure all the way around one circle, and our hexagon, as you travel around that thing, is broken evenly into 6 pieces. That means that measurement around the center point of the circle, that 360 is divided evenly 6 ways. Okay, so what we end up with is 6 angle measurements inside of there that measure exactly 60 degrees each. Okay, so I've got all these little angle congruency marks in there now, so all those 6 angle measurements are the same. Okay. Now, all of the radii are going to be congruent, right? Because it doesn't matter which corner point you measure to from the center. It's the same distance to each of the corner points. So if all of your radii are also congruent, well, there I threw in a bunch of tick marks for us. Okay. So we got a lot of stuff happening in here. Now, basic property of triangles. Okay, what does it mean in a triangle if you have two sides of a triangle that are congruent to each other? What does it mean about the angles across the triangle? They're going to be congruent also, right? Because there's a connection between the side lengths and the angle measurement. So if you're looking inside of one of these little triangles, you got two tick marks on each side. What's that mean about the angles across from them? It means they are going to be congruent. Okay. And if you get thinking about the relationship in a triangle that all the angles have to add up to 180 degrees, well, we've got 60 degrees used up inside of each of these little triangles already. That leaves 120 degrees to be shared by the other two angles in the triangle. We just said it has to be shared equally. So the 120 gets divided into two, so we get more 60-degree angles. So look what happens. Every angle that you go to anywhere in any of these triangles ends up being 60 degrees. Okay, so those base angles in each triangle turn out to be the same measurement as the vertex angle. So the third side must also be congruent to the other side. Because look, in your triangle, you've got all three angles congruent. If all three angles are congruent, what does that mean about the side lengths? All three sides must be congruent as well. So it's not just one tick mark on each of the radii. Based on that triangle relationship, now it's a tick marks on each of the sides as well. Well, other than looking like a snowflake inside of there, look at what actually just happened. You've got a regular hexagon, meaning all of the sides and all of the angles in the hexagon are going to be the same. But look at each of the triangles now. Each of the little triangles is also equilateral and equiangular. Okay, so each triangle has all its sides the same and all of its angles the same. In other words, a regular hexagon is built out of 6 regular triangles. Okay, if you look closer at each of those triangles and you draw in an apothem inside of the hexagon, it would look something like this. I pulled one of the little triangles out. Here's the center point up here at this peak. Here's the side of your hexagon down here at the bottom. I dropped an apothem inside of that hexagon. Okay. When you do that, look what ends up happening. If it was 60, 60, 60 all the way around the blue triangle, the apothem came down through there. This is one of those old properties. We have an isosceles triangle that now has an altitude in it, because an altitude is always perpendicular. Okay, and remember the rule, if you have an isosceles triangle and you end up with an altitude, it's also an angle bisector, it's also a median, it's also a perpendicular bisector. In short, this angle up top here at the center got bisected. So that 60 broke into two 30s. Look at these triangles now. 30s, 60s, 90s, 30, 60, 90. And we have those special rules on the formula chart that talk to us about the 30, 60, 90. Remember, hypotenuse is going to be the short leg times 2. Okay, hypotenuse is twice as big as the short leg. And the long leg is whatever the short leg is times the square root of 3. Okay, and those formulas are on the formula chart. But this is a very, very dangerous shape for this particular reason, because if they just go, hey, here's a regular hexagon, when they put those two words together, our brains need to go, oh man, okay, regular hexagon. That means when I draw in all the diameters, I end up with 6 regular triangles. And if I throw an apothem in there, then it breaks those regular triangles into 30, 60, 90 triangles. So it's not just, you know, Pythagorean Theorem that you got going on in there. It's not just SOHCAHTOA you got going on in there. You also got 30, 60, 90s going on in there. Okay, so a regular hexagon, there's a lot of formulas, which means there's a lot of things they can do to us. Okay, they can give us one piece of information and who knows where it's going to be, but they can ask us just about anything under the sun, giving us one little piece of information on a hexagon. So just want to kind of introduce you to the hexagon. That's one of the shapes that, honestly, I hope you don't see one on the test, because they can be tough. Another shape we're going to look at is the regular polygon, the regular quadrilateral, which is the square. Okay, and again, I'm going to go through this pretty quick. So if you really want to look at it and copy notes down on it, you probably need to look at it on Edmodo. But something else happens with the regular quadrilateral. Something happens with the square when we start dropping diagonals or diameters into it. Okay, so if we throw a diameter into a square, well, look what just happened. In a square, all of our angles are 90 degrees. So what do you think just happened here at these corner points where the diameter just showed up? It bisected those angles. Okay, if it bisected those angles, then those 90s were split in half. Now we have 45, 45, 90. Okay, 45, 45, 90. There's also rules about that on the formula chart. The hypotenuse equals the leg times the square root of 2. So the two triangles that are generated are 45, 45, 90s with 90-degree angles in the corners of the square. But look what happens when you throw both diameters in there. Okay, you get both diameters in there. Look what happened on the other side now. The other two 90s just got split in half as well. So now you got 45 in one corner, you got 45 in the other corner, and you got 90 at the intersection between the two diagonals because the diagonals of a square are perpendicular. Diagonals of a rhombus are perpendicular. So you got 45, 45, 90, 45, 45, 90, 45, 45, 90, 45, 45, 90. So the two diameters actually split the square into four 45, 45, 90s. And actually, this gets worse and worse and worse from there. Actually, the appearance of 45, 45, 90s will continue as long as we draw in altitudes of the triangles of the square. That's to say, if I were to come across here and here, you know what just happened to those four red 45, 45, 90 triangles? They just got split into 8 smaller 45, 45, 90 triangles. And if we came across here, then it got split into 16 45, 45, 90 triangles. And if you did this, well, there's 32 of them now. Okay, and this will happen over and over and over again as long as you continue to put altitudes inside of all those little triangles. Okay, so once again, this is, I don't mind if they give us squares, but I hope they don't give us too many questions that might deal with it being a regular polygon, because again, there's a lot of things they can do to us using one little piece of information. Okay, so two shapes to watch out for. Let's look at some examples of just some regular polygons and see if we can figure out how they work. Find the area of the following regular polygon. All right, well, we're going to begin this area question just like we've been beginning any area question that we've come across. And the first thing that we ask is, do we have a formula that deals with this shape? Okay, well, it's a regular polygon. Yes, we have a formula. And again, very much not sure if it's going to be on the formula chart or not. So we're going to get it committed to memory just in case. 1/2 times the apothem times the perimeter. Okay. We'll have a look into the figure. Do we have enough information to determine, number one, what the apothem is, and number two, what the perimeter is going to be? What do you think? Do we have the apothem? Do we have the short distance from the center point of the figure directly over to the side? Yes, we do. Okay, and we know this because it's perpendicular. It's coming directly over, makes contact perpendicular. So yes, we have the apothem. How about the perimeter? Do we have the perimeter? Yes and no, right? Did they give us the perimeter? No. Did they give us enough information to simply find the perimeter? Yeah, they did. Okay, they gave us one side length as 6. Does that mean that every side length is 6? Yes, it does. Okay, because if a figure is regular, that means that all the angles are congruent, but also all these sides are congruent. So if they're going to hand us one side of a regular polygon, they handed us all the sides. So plugging into the formula is really quite simple in this case. 1/2 is built into the formula, so we just leave it alone. The apothem was able to be pulled directly out of the diagram, 4, and the perimeter was calculated easy enough by saying that each side length is 6 units long, and there are 5 side lengths. From there, all we have to do is clean up the math a little bit. 1/2 times 4 times 6 times 5. Well, half of 4 is 2, times 6 is 12, and 12 times 5 is 60. And it will be a unit squared, whatever the units are, inches, centimeters, millimeters, pink flamingos, whatever they are. They will be squared. Okay, but it's entirely possible that if they bring a regular polygon to our doorstep, that they may not hand us everything that we need to know. So let's look at a different situation. All right, well, it's the same situation as before. What we do is we ask ourselves, first and foremost, do we have a formula that goes along with this polygon? Do we have one? Yes, what's the formula? I know it's brand new, but have a look. We need to get it committed to memory. 1/2 times A times P, 1/2 times the apothem times the perimeter. Okay. Well, have a look into the diagram. Did they provide us with the apothem? Yes. What is it? No? Would you make up my mind? Okay. April's arguing with herself. Anybody want to join in? No. Do we have the apothem this time? No, we don't. What do we have? Radius. Absolutely. We have the radius, but not the apothem. Okay. How about the perimeter? Yeah, they didn't give it to us, but they gave enough information for us to find it pretty easily, right? Okay. So what are we going to do? What's going to be our strategy as far as finding the apothem? Okay, we can find the perimeter. How would finding the perimeter help you out finding the apothem? You might be right, just asking. Pythagorean theorem, right? Okay, that's an excellent. If you can find a right triangle, then you've got a squared plus b squared equals c squared. You've got SOHCAHTOA. You've got all kinds of things if we can find a right triangle. Well, we've got a right triangle in there using the radius and the apothem and half of a side length. Now, what about half of a side length? Wouldn't it be nice to have that? It is 5, absolutely. Okay, and that's one of the properties of an apothem. It's going to come over and it's going to bisect that side. So if you got 10 units on each side, then you got 5 units for each half a side. Okay, good. Sounds like we got a strategy. Okay, perimeter was going to be easy. Okay, we got 10 units on each side, and it's going to be 8 sides. How do we know that each of the sides is going to be congruent? Yeah, they threw the word regular at us. When they throw the word regular at us, we know that we're equiangular and equilateral. Okay, so easy enough there. Okay, now we're going to have to get a little sidetracked here so we can figure out what's going on with the apothem. Okay, but as y'all have already pointed out, we had one of the legs, 5. We had the hypotenuse, 13. And if we knew what was going on with the apothem in there, then we'd be good to go. Just out of curiosity, anybody know what this missing value is going to be without working it out? Want to get out of the way so y'all can see. Anybody know what the missing one's going to be? 12? How'd you get that? Did you actually do all that math in your head? Good job. All right. Anybody anybody can get it? Anybody know it any other way? No? The calculator. Okay, good. Okay, hopefully your batteries aren't dead. Okay. 5 and a 13. There is another one of those triangles where it's all 3 whole numbers. What's that called? We're right triangle and it's all 3 whole numbers on the side lengths? Uh-oh. A Pythagorean triple. Yes, thank you. Okay. If you solve this guy out, and we ought to start recognizing this one a little bit. The second most basic Pythagorean triple that's out there is the 5, 12, 13. 5, 12, 13. You'll see it. Okay. The first one being the 3, 4, 5. We see the 3, 4, 5 quite a bit. We're going to see the 5, 12, 13 quite a bit also. Okay. Pythagorean triple. All three side lengths are whole numbers. Okay. All right. Now, why did we solve for the apothem? Is this the answer to our question? No, it's not. Why did we solve for it? Because it was missing right there. Okay, it was the only thing that was missing from being able to calculate the area. It's not missing anymore. So now we can jump back to the area formula, plug in our new value for the apothem, And now we can get back to Adrian's calculator with the dead batteries and figure out what this value actually is. Let's see what we do have here. Half of 12 is 6. What's 6 times 8? 48. And then times 10 throws a 0 on the end of that. 480. And again, whatever the units are, millimeters, kilometers, astronauts, whatever, they will be squared. Okay, so again, it's a multi-step problem, so beware. Don't be surprised if you see 12 as one of the answers on the test. It's just not the answer to the question. Okay, so make sure you're actually answering the question that's addressed. Okay, we're going to look at one more, and then I'll quit badgering you about stuff. Let's have a look at this guy. Okay, so let's have a look at this guy. Okay, it is a regular polygon. It's got 4 sides, so it's a square. Okay, now formula for regular polygon. Now it's a regular polygon. We've got the formula 1/2 times the apothem times the perimeter. Now, is that the only formula we have for finding the area of a square? No. We could use the side squared formula. We could use the 1/2 times d1 times d2 formula. There's a lot of different things that we could do. Okay, but since we're talking regular polygons, let's go ahead and look at this one. Okay, 1/2 times the apothem times the perimeter. Did they give you the apothem this time? No, no apothem. Did they give us the perimeter this time? Also did not give us information about the perimeter. Okay, so what we're going to need to do is we're going to need to be able to figure out what is going on with possibly getting apothem or perimeter. Okay, be great if we had a right triangle to start working from, so we will build one. We're going to need the apothem anyway. Okay, so I'm just going to go ahead and install it in the problem. Okay. Now, there's a lot of ways to get this information from the inside out. Okay. We could do Pythagorean Theorem. Okay. We could do Pythagorean Theorem. Okay. And remember what we said just a few minutes ago. What happens when you start breaking these guys up in a square? You end up with a whole bunch of 45, 45, 90 right triangles. If that's the case, if these guys are congruent and that's the apothem, okay, since these guys are congruent, that means that the sides across from them are going to be congruent as well. So whatever the apothem is, that little half of that side is also going to be. So if we plug into Pythagorean theorem, we could go a squared plus another a squared equals 2 squared, and we could solve Pythagorean theorem from there. Okay, that's an option. Or if you know that you have 45-degree angles in there, you could take the trigonometry route. I misspelled SOHCAHTOA. That's not good. You could take the 45-degree angles that you have in there, use SOHCAHTOA to help you figure out what's going on with your missing sides. That's certainly an option. If you have 45, 45, 90s in there, which we do, then we have rules that go along with that, like the hypotenuse equals the leg times the square root of 2. We could find it out like that. They're all good. Okay, they're all good. We can do anything we want. Personally, I'll just go ahead and finish off the Pythagorean theorem here. We got an a squared, we got another a squared. That is 2a squareds. That equals 4. Divide this 2 away from our a squared, and you end up with a squared equals 2. We don't want a squared, we just want a. So if we take the square root of both sides, then we end up with a equals the square root of 2. Okay, so all I did there was just follow through Pythagorean theorem. And whether you decided to do it with SOHCAHTOA and work it out, or with the 45, 45, 90 rule and work it out, you're going to end up with the same value in all 3 locations. Okay, well that's good. We've got that guy. Okay, we now know what the apothem is trying to be. Square root of 2, square root of 2. Okay. Now what about the perimeter? Okay. Well, if this little guy here on the perimeter, that little a is square root of 2, then what do you think about this guy down here below it? Also square root of 2. Okay. The question is, if it's square root of 2 and square root of 2, then how much is an entire side length? Yeah. Well, you got a square root of 2, and then you've got another square root of 2. So what do you have? You have 2 square roots of 2. Okay, it's like saying you got one calculator plus another calculator. How many calculators do you have? Well, you have 2 calculators. Okay, so the sides are actually 2 square root of 2, and that's going to carry on all the way around. So what is the perimeter going to be? Eight square roots of 2, exactly. Okay. Now this is looking awfully ugly right now. Okay, but it's just a multiplication problem. And remember, with multiplication, whole numbers want to combine with other whole numbers. Radicals want to combine with other radicals. So here we go. Numbers. 1/2 times 8. What's 1/2 times 8? 4. Square root of 2 times square root of 2. What's that? Square root of 4. What's the square root of 4? 2. 4 times 2 is 8. See how tricky some of these can get? Okay, it can get kind of ugly sometimes, but it's just numbers. Okay, it's just numbers. It takes a lot of steps, but which one step was all that difficult? They're not. There's just a lot of them. Okay, so this is the way regular polygons work. You can see why I'm hoping that they don't give us a square that we have to treat like a regular polygon. I'm hoping we can use one of our other formulas, which actually the formula on the diagonals would have been a great one to use on this one rather than going through the regular polygon formula. But anyway, okay, that is how we find the formula, or how we find the area of regular polygons. We got some practice problems, so let's get to it.